blade diameter is 0.75 meters. Its rotational speed being 3500 rpm. Its rotational speed being 3500 rpm. The absolute velocity of fluid, discharging from a nozzle, inclined at 20 degree, to the plane of the wheel is 275 meter per second. To the plane of the wheel is 275 meter per second. If the utilization factor is 0.9, and the relative velocity at rotor exit is 0.9 times that at the inlet. 0.9 times that at the inlet. Find the inlet and exit rotor angle. Find the inlet and exit rotor angle. Also find the power output from the stage. For a mass flow rate of 2 kg per second. And axial thrust on the shaft. Okay, while coming to the problem statement, so clearly they given it is an impulse turbine. Okay, impulse turbine is nothing but the degree of reaction is 0. Okay, impulse turbine is nothing but the degree of reaction 0. But if the degree of reaction 0, okay, what is the condition? So relative velocity VR1 is equals to VR2. The relative velocity VR1 is equals to VR2. But in the problem statement here you can see. Okay, in the problem statement, the given the relative velocity at rotor exit is 0.9 times that at the inlet. So this is very important. Okay, this is very important. Please underline here. Okay, so underline here. So they given the relative velocity at rotor exit. So that is VR2. Okay, they given the relative velocity VR2 is equals to 0.9 times VR1. Okay, 0.9 times VR1. So in the problem statement they given. If they not given, so directly we can take. So VR1 is equals to VR2. Okay, but here they not mentioned. So here they mentioned. Okay, so VR2 is equals to 0.9 VR1. Okay, so this is very important. Okay, then we have to find out the inlet rotor angle. Rotor angle is nothing but okay, beta 1 and beta 2. Okay, so this is very important in this case. Got it? Yeah. So they given the diameter as 0.75 meter and the speed being 3500 rpm. The absolute velocity of the fluid discharging from the nozzle. So this means alpha 1 is 20 degree to the plane of the wheel. It means it is an absolute velocity v1. So it is an 275 meter per second. And utilization factor, that is epsilon 0.9, and relative velocity Vr2 is equals to zero point 0.9 Vr1. So we have to find out beta 1, beta 2. So also we have to find out what is the power output. Okay, we have to find out what is P. For that they given the mass flow rate as 2 kg per second. And we have to find out what is the axial thrust. We have to find out Ft. Okay, we have to find out Ft. So that is the axial thrust on the shaft. Okay, so this is the data. Okay, so before solving, okay, first write the inlet and outlet velocity triangle. Okay, so this is the inlet and outlet velocity triangle, the general form. Okay, later we'll going to check. Okay, later we'll going to check. So whether this velocity triangle remains same or this velocity triangle remains same, or we have to modify. Okay, so first write the initial velocity triangle here. So next, here they given the tangential speed of the rotor. So U is equals to pi dn divided by 60, because we have only one diameter. So we can take it as a pi dn divided by 60. So find what is u. So calculate what is u. So if we calculate it, tell what is the u value. So if we calculate it, okay, tell what is the u value. Okay, got the value. So u is equals to 137.44. Yeah, okay. Yeah. Similarly, find, so what is VF1 from the inlet velocity triangle? So we know the nozzle angle alpha 1, okay, and know the absolute velocity. So we have to find out what is VF1. So sine alpha 1 is opposite by hypotenuse. So find what is VF1. So find what is VF1. Next, similarly, find out what is VU1 from the inlet velocity triangle. Okay, we want what is VU1 from the inlet velocity triangle. So here we know the nozzle angle. Okay, and know we know what is absolute velocity V1. So cos alpha 1 is adjacent by hypotenuse. So find out what is VU1. So please calculate everyone. See, once you calculated, you just give the confirmation. Next, I'll move for the next step. So VF1, okay, it is in a 94.06 meter per second. I hope you got this value. So similarly, find out from the inlet velocity triangle VU1. So similarly, find out what is VU1. So VU1 has 258.42 meter per second. Okay. So from the inlet velocity triangle, okay, for this apply the Pythagoras rule and find out what is a VF1. Sorry, find out what is VR1, the relative velocity at inlet. By using this velocity triangle, from the inlet velocity triangle, right angle triangle, so find out what is VR1. Okay, find out what is VR1. So apply the Pythagoras rule, we'll get VR1 square is equals to VF1 square and this distance. So it is in a VU1 minus U whole square. So VU1 is 25.8, okay, 258, correct. 258, yes, correct. Yeah, apply the Pythagoras rule for the inlet velocity triangle, this right angle triangle, and find out what is VR1. Find out what is VR1. So we'll get VR1 is equals to 153.24 meter per second. So we'll get VR1 as 153 point. Okay. So next find out what is beta 1. Find out beta 1 from inlet velocity triangle. So we know tan beta 1. Okay, it is an opposite by adjacent. So opposite we'll get VF1. So opposite is Vf1, okay, and adjacent is this distance. So this distance is Vu1 minus U. Okay, Vu1 minus U. So find out what is beta 1. So find out what is beta 1. So we know Vf1 value. So already we calculated, and we know what is Vu1. Find what is beta 1. So that is rotor blade angle at inlet. Okay, rotor blade angle at inlet. So this is the rotor blade angle at inlet. So I hope you got beta 1 as 37.86 degrees. So next we'll go for outlet velocity triangle. But before going to that, okay, in the problem statement, they given the utilization factor. Okay, they given what is the epsilon. The utilization factor is 0.9. And we know the relationship between utilization factor and degree of reaction R by using that equation. So epsilon is equals to V1 square minus V2 square divided by V1 square minus R into V2 square. Okay, but R is equals to 0. The reason is impulse turbine. The reason is impulse turbine. So R is equals to 0. Okay, then by applying all this, okay, we know epsilon and we know absolute velocity. Okay, we know the absolute velocity at inlet. So by using this data, we can find out what is V2. Okay, we can find out what is V2. So use this equation. So epsilon is equals to V1 square minus V2 square by V1 square minus R into V2 square, but degree of reaction is 0. The reason is impulse turbine. Okay, then find out what is V2. So V2 you'll get 86.96 meter per second. So V2 is 86.96 meter per second. Next, find out what is VR2. Find out what is VR2 because this also they given in the data. The relative velocity at outlet is equals to 0.9 times VR1. Okay, the relative velocity at outlet is 0.9 times VR1. So already we know VR1. So find out what is the relative velocity at outlet. Relative velocity at outlet. So V2 86.96. Yes. Similarly, find VR2. But here, before going to this from outlet velocity triangle, okay, so before going to this, because here we have to find out what is VU2. Okay, so here we required VU2. Even in power also, okay, in power output also, okay, we required VU2. Okay, so before calculating this VU2, whatever this velocity triangle, okay, it is not suitable. because here I don't know what is VF2 and I don't know what is VU2 and all. And even I don't know alpha 2 and I don't know beta 2. Okay, so for this, we can go for, or else here only I will show. So I'll going to use this velocity triangle. Okay, so I'll going to use this velocity triangle. Because see here, whatever the outlet velocity triangle, so here we'll get two right angle triangles. By using these two right angle triangles, it's okay. So we can use Pythagoras rule for this and the Pythagoras rule for this velocity triangle. Then we can equate, okay, these two equations. So in that V of whatever the V of 2, okay, it will get cancelled. Okay, V of 2, it will get cancelled. Then whatever the direction, it will going to changes. Okay, then here also I will going to show once again. Okay, here also I'm going to show the once again. I'll come for here. I'll come for here. So if we're going to use that velocity triangles, okay, so see, by using this, okay, by using this, so here VF, so we can apply the Pythagoras rule for this, and we're going to apply the Pythagoras rule for this velocity triangle. So here I'm going to show HEF one velocity triangle and HGF is the another velocity triangle. So here we will get the two velocity triangles. Okay, here we'll get the two velocity triangles. So by in this, okay, so we can take VF2. Okay, it is in a common. So and we have to equate these two equations. Then if we equate these two equations, then we will get what is VU2. Okay, what is VU2? So that we're going to see here. Say I'm going to use V of 2 square is equals to V2 square minus VU2 square, and V of 2 square is equals to VR2 square minus VU2 plus U2 whole square. So here you can see, because there is a no another option to calculate this one. So instead of writing the outlet velocity triangle like this, okay, directly I can write, but I don't know. So whether it will going to change or not. But in this stage, okay, we don't know how to calculate VU2. So that is the better option. We'll go for this velocity triangle. Okay, this velocity triangle. Okay, you just calculate what is the value of VU2. Just calculate what is the value of VU2. So after equating all this, okay, whatever here we have, so minus VU2, and here it is on a minus VU2, it will get cancelled. Okay, so VU2, it will get cancelled, and finally we will get minus 2 times VU2 into U2 is equals to V2 square minus VR2 square plus U2 square. Okay, but here I want VU2. See VU2, okay, so we are getting it is in a negative value. So this is very important. Whatever this negative value, so we have to modify the velocity triangle to this. Okay, we have to modify the velocity triangle to this. Okay, the reason is only the negative sign. So here we got negative sign. So initially the outlet velocity triangle in this manner. Okay, the outlet velocity triangle is in this manner, but whatever this vu2 we are getting a negative sign. So this whatever v2, okay, so the direction it will changes. So here in the vu2 negative sign indicating it is only for the, okay, only for the direction. This is very 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 important because later you have to calculate the power. Okay, so here, sir, we got negative value, so then directly I can take negative. No, negative sign indicating, okay, we have to change the direction. Okay, we have to change the direction. So for that reason, okay, so we have to calculate VU2. So here negative value, so negative indicating, so changing the direction. Okay, so I hope you got VU2 as minus 27.03 meter per second. Okay, I hope you got. So VU2 as 27.03 meter per second. So once you got negative value VU2, so please modify the velocity triangle and change the direction. So initially it is in the opposite direction, but so VU1 as well as VU2, okay, it is in a same direction. Okay, both are in a same direction. Got it? So this is one is very very important. So next find out beta angle. Next, find out what is the beta 2 angle. So that is a rotor blade angle at outlet. So cos beta 2, okay, it is an adjacent by hypotenuse. So here I did mistake. Instead of taking negative, okay, I took positive. So please make correction. So it is an adjacent by hypotenuse. So what is adjacent? I want this distance. Okay, I want this distance. So U2 minus VU2 divided by, so hypotenuse is VR2. Okay, because this is the beta angle. So please make correction this. So U2 minus VU2 divided by VR2. Okay, so we'll get beta 2 as 36.61 degree. So I hope you got this value. So beta 2 is 36.61. So next find out VF2 from outlet velocity triangle. So now we know the beta 2 angle. Okay, sine beta 2 is equals to opposite by hypotenuse. So opposite is VF2 and hypotenuse is VR2. Okay, sine beta 2 is opposite by hypotenuse. So opposite VF2, hypotenuse VR2. Okay, find out what is VF2 because we have to find out axial thrust. Okay, we want to find out axial thrust here. Okay, so for that, so we required VF2. Okay, so VF2 is equals to 82.65 meter per second. 82.65 meter per second. So 82.65 meter per second. So VF2 is equals to 82.65 meter per second. So next, we have to find out the power. So P is equals to M into VU1 U1 minus VU2 U2 by GC. GC is only unit conversion factor. So U1 is equals to U2. So once again, I can write this equation as M into U. So VU1 minus VU2. See why I took negative sign here? Because VU1 as well as VU2, okay, it is in same direction. VU1 as well as VU2, okay, when it is in a same direction, then we will going to take it as a negative. If it is in a opposite direction, then we can take it as a positive. And then we can take it as in a positive. So find what is power. So P is equals to, we get 63.6 kilowatts. So P is equals to 63.6 kilowatts. So next we want to find out the axial thrust. Okay, we want to find out what is the axial thrust. So for that, so axial component VF1 and VF2. So while resolving the absolute velocity V1, we'll get the two components. So one is an axial component, another one is an radial component. So axial components VF1 and VF2. Okay, so the formula is Fa is equals to M into VF1 minus VF2. So Fa is equals to M into VF1 minus VF2. So we'll get the axial thrust as 22.82 newtons. Okay, F2 is equals to, sorry, Fa is equals to 22.82 newtons. Okay, I hope you got this value. So P is equals to 63.6 kilowatts and axial thrust Fa is equals to 22.82 newtons. Okay, so in this problem, okay, you have to take care only here. Okay, you have to take care only here because the negative value. So once you got the negative value, so we're going to change the direction, VU to direction. So that is one modification in this problem. So I hope you cleared that problem. Okay. So if you have any doubt, you can ask. Okay, no doubt. Okay. Okay, I'll going to continue at 1 o'clock. Okay, I'll going to continue at 1 o'clock. Next, we'll move for next problem. So the problem statement is in a mixed flow turbo machine. In a mixed flow turbo machine, fluid enters such that absolute velocity is axial at inlet, such that the absolute velocity is axial at inlet and relative velocity is radial at outlet. So please underline these words. Absolute velocity is axial at inlet. So please underline for this. The absolute velocity is axial at inlet and relative velocity is radial at outlet. What is the degree of reaction? What is the degree of reaction and energy input to the fluid? Energy input to the fluid if the relative velocity at outlet is same as the tangential blade speed at inlet. If the relative velocity at outlet is same as the tangential blade speed at inlet, the following data may be used. The following data may be used. Inlet diameter is 16 centimeter. Exit diameter is 50 centimeter. Speed is 3000 RPM. Blade angle at inlet is 45 degree. Blade angle at inlet is 45 degree. 45 degree. Excuse. See, in this problem, so please understand the statement. Okay, so they given it is a mixed flow turbo machine. So fluid enters such that the absolute velocity is axial at inlet. Such that the absolute velocity is axial at inlet and the relative velocity is radial at outlet. The relative velocity is radial at outlet. So please, anyone can tell what is that statement means? So you can unmute. So please answer anyone. So how we can write the velocity triangle for that statement? So unmute anyone. So unmute anyone. Manjunath. 70 me 069.
Yes, sir.
So please tell how we can write the velocity triangle for this statement. So absolute velocity is nothing but v1, right?
Yes, sir.
Okay, so here the given absolute velocity is axial at inlet. Okay, axial is nothing but it is a perpendicular, right?
Yes, sir.
So we can write V1 is equals to V of 1. So here I written VA1, both are same. So V1 is equals to V of 1. And next they given the relative velocity is radial at outlet. So relative velocity means VR2 because they give mentioned the VR2. So it is an a radial. So that is VR2 is equals to VF2. Clear?
Yes, sir.
Okay. As per this condition, okay, as per this condition, we have to draw the velocity triangle. Okay, so V1 is equals to VF1 and VR2 is equals to VF2 as per the problem statement. So what is the degree of reaction? So we have to find out what is R and energy input to the fluid. So we have to find out what is E. If if the relative velocity at outlet is same as the tangential blade speed at inlet. Okay, so they given relative velocity at outlet. So VR2 is equals to, okay, VR2 is equals to is same as the tangential blade speed at inlet. So that is U1. So VR2 is equals to U1 because in the problem statement itself they given. Okay, as per this statement, okay, we're going to take VR2 is equals to U1. So the following data may be used. Inlet diameter is 16 centimeter, outlet diameter or exit diameter is 50 centimeter, and speed, so 3000 RPM, and blade angle at inlet is 45 degree. So beta 1 is equals to 45 degree. Okay, so before solution, okay, draw the inlet and outlet velocity triangle as per the condition. Okay, as per the condition. So draw this velocity triangle. If you have any doubt, you can ask. Okay, if you have any doubt, you can ask. So this is the inlet velocity triangle and this is the outlet velocity triangle. See, V1 is equals to VA1 means, okay, so here whatever we have VU1, okay, it is completely zero. Okay, it is completely zero because V1, the absolute velocity is falling on VF1. Okay, so alpha 1 is equals to 90 degree. So alpha 1 is equals to 90 degree. So V1 is equals to VF1 and VU1 is equals to 0. Inlet velocity triangle. So next, while coming to the outlet velocity triangle, so here clearly they given VR2 is equals to VF2. Okay, VR2 is equals to VF2. Okay, it means whatever the beta 2 blade angle at outlet is 90 degree. Okay, blade angle at outlet is 90 degree. Okay, then U2 is equals to VU2. Okay, U2 is equals to VU2. U2 is equals to VU2. So this is the inlet and outlet velocity triangle as per the condition. Okay, as per the condition given. So here they given, they mentioned D1 and D2. With respect to this, we're going to find out the blade speed velocity at inlet and outlet. So U1 is equals to pi D1n divided by 60 and U2 is equals to pi D2n divided by 60. So find out U1 and U2. So calculate U1 and U2. Calculate U1 and U2. Calculate U1 and U2. Okay, Abhishek, 17M is 004. So I hope you got this value. So U1 is equals to 25.13 meter per second. U2 is equals to 78.53 meter per second.
Yes, sir.
Yeah, okay. So next, from inlet velocity triangle, find out what is VR1. From the inlet velocity triangle, find out VR1, because we know what is the beta 1. Okay, we know what is the beta 1. So cos beta 1 is adjacent by hypotenuse. So U1 by VR1. So find out what is VR1 value. I hope you got VR1 is equals to 35.54 meter per second. So next, from the inlet velocity triangle only, okay, apply the Pythagoras rule. So VR1 square is equals to V1 square plus U1 square. So find out what is V1, absolute velocity. Find out what is V1. So I hope you got V1 is equals to 25.13 meter per second. So V1 is equals to 25.13 meter per second. Similarly, from outlet velocity triangle, find out what is V2. Find out what is V2. So if you have any doubt, VR2 square, okay. So VR2 square means the relative velocity at outlet as per the statement. So UR2 is equals to U1. The relative velocity at outlet is same as the tangential blade speed at inlet. So what is the tangential blade speed at inlet? 25.13 meter per second. So I took the same. Okay, so you will get V2. So V2 is equals to 82.26 meter per second. 82.26 meter per second. So next we have to find out the energy input to the fluid. Okay, so energy input to the fluid. So that is the Euler's turbine equation. So E is equals to, so VU1 U1 minus VU2 U2. So E is equals to VU1 U1 minus VU2 U2. So VU1 is equals to 0. The reason is this one. If the absolute velocity is axially or radially, whatever the absolute velocity is axially or radially, so VU1 will become 0. So this term is 0. So then E is equals to, find the value. I think you will get the negative value here. So I think E is equals to minus 6.168 joules per kg. The negative sign indicates it is a power absorbing turbo machines. Okay, it is a power absorbing turbo machines. Then we have to find out the degree of reaction. So next, find out what R is equals to 0.5. So R is equals to, so half into U1 square minus U2 square plus VR2 square minus VR1 square divided by half into U1 square minus U2 square plus V1 square minus V2 square plus VR2 square minus VR1 square. If you substitute U1 U2 VR1 VR2 V1 V2, okay, you will get R is equals to 0.5. Okay, R is equals to 0.5. Okay, if you have any doubt, okay, you can ask. If you have any doubt, you can ask. So there is a no doubt. Yeah. So I covered almost all type of problems. Okay, I covered all type of problems. Okay, to calculate alpha 1, to calculate beta 1, beta 2. Okay, and if the conditions, okay, if they given the conditions, how to draw the velocity triangles. Okay, so next year, how to change the directions. Okay, so I covered all type of problems here. Okay, so if you have any doubt, So note down your doubts. Okay, so you can ask in the next class. So, and I'll going to wind up. Okay, the first unit. So I'll going to wind up the first unit. So next I'll going to start unit 2. So here you can see your syllabus. Okay. So before going to the second unit, okay, just I'll going to glance unit 1. So one is an a defined turbo machine. So parts, classifications, comparison with positive displacement machine. So that is the difference between turbo machines and positive displacement machine. Dimensionless parameters. So using Buckingham's pi theorem. And here you can see the specific speed, model studies, and simple numericals on that. Okay, simple numericals on that. So that is on model studies. So prototype and model. Next, Euler's turbine equation, alternate form of Euler's turbine equations, and components of the energy transfer. Okay, components of the energy transfer. So next, degree of reaction. Next, here in the general analysis of pumps and compressors. So what is radial flow, axial flow? So type of velocity diagram. In brief, combined velocity diagram with common apex and common base. Okay, how to draw the velocity triangle by common apex and common base. Next, general analysis of turbines, radial flow, axial flow, utilization factor, relation between degree of reaction and utilization factor. Okay, expression for maximum utilization factor for axial and radial flow, and problems. Okay, problems. So I covered all, and even problems also for different cases. So next, unit 2 design a hydraulic turbines. So here you'll get the classifications and the general layout of hydraulic power station or a power plant. And again, in that, what are the different rates as well as efficiency. So here you can see Pelton wheel and the Francis turbine. Okay, so Pelton wheel, it is an example for impulse turbine, and in the reaction turbine we'll get the Francis turbine as well as one more is Kaplan turbine, but in your syllabus you don't have the Kaplan turbine, you have only the Francis turbine. So in this unit you will get only one derivation on Pelton turbine. Okay, here you can see the work done equation. Okay, and condition for maximum hydraulic efficiency. So this is your derivation. You have only one derivation in unit 2. Okay, and there is a no your derivation on Francis turbine. Okay, you should know what is the velocity triangle for Francis turbine and the problems on Francis turbine. Okay, here the derivation and how to draw the velocity triangle for Pelton wheel and problems. Okay, so I'll going to start in the next class. Okay, so unit 2. So once again, I'm telling if you have any doubt, okay, in the unit 1, okay, note down your doubt and you can ask in the next class. Okay, you can ask in the next class. Thank you.